for some integer. Okay, now this is important because you are introducing a new variable unknown into your equation in your proof. You have to state what is it, define it. So we just say it's some random number. In this case, a random integer. Then we just show that n square equals to n square, on squaring it on the left hand side, and we're also squaring it on the right hand side. And what we're going to get is n square equals to 4k square plus 2, this is 2, right? So this is again 4k plus 1, right? And then remember, our end goal is to have n squares odd. So we need to factor this in the form that it is odd. So we can also say, then the next step would be n square equals to 4. Then you have it as k square plus k plus 1. And this is the same as n square equals 2j plus 1. Right? And there's no more space, but normally j, I'll put there as j equals to 2k plus k. Right? To show I want it just in this form of an odd number, or if our unit number is 2k. So when n square equals to 2j plus 1, we say that this is an odd outcome. Hence, our proof is complete. So you have to conclude there lah. Therefore, proven true. Therefore, proven true. Right? That n square is odd whenever n is odd. Understand? So always remember what's the end goal and try to solve it until you reach that point there like that. Right? To represent it in that form. So this is the case of question. Unwriting the screen. So the same thing I showed you earlier. So they show that r equals to 2k squared plus 2k. I did it in the other way. It's still the same thing because we say that the j is this. So, you know, in the form of 2r plus 1 or 2j plus 1, it's still the same result. A real number r is a rational number if there exists p and q such that q is not equal to 0 because there's a denominator. And finally, what we're trying to say is that r equals to p divided by q. So you're trying to say that a real number r is considered as a rational number only because you can find that value from the division of two integers. Right? So you have an integer p, integer q, right? They cannot be 0, of course another division doesn't work. And you have not an integer, this is a non-integer, it's a real number. So that real number which is rational is normally your round numbers, right? 2, 3, 4, 5, 6, and any other real number because an integer is a subset of a real number. So prove that the sum of two rational numbers is rational. How do you go about doing this one then? It is straightforward. Again, I think I don't want to rewrite it. So we have now with the definition of a rational number, r, remember r is not an integer, r is a real number. That real number is represented by two other real numbers. Is it going to the next slide? So you have r having equals to p over q, and then the question is the sum of two rational numbers. So let's say we have one rational number r, and then we have another rational number s. And you say that r plus s equals to a rational number. So then t has to be also a rational number. So if prove that the sum of two rational numbers is rational, so we say that r plus s equals to t. Now, in this question here, you ask, where is the p, where is the q? It doesn't look like an implication question. So the question here is not given explicitly your p. That is for you to state that you're assuming p to be, you have these three and these three are rational number. And by the definition in number theory, blah, 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 R is represented by P or Q. Then you do one new one for S over T. Oh, we don't need to use the T here, lah. So we just call it a rational number because they don't want to add that additional step, which is fine. So you just say that it has to be a rational number. So you have a case of T over Q. R and S is the same as P over Q plus T over U. Can I zoom in here? I can't zoom in here. Only on the main screen. And then just your basic algebra, unless you get a form of U over V. And we know that U over V is also in the form of an integer divided by another integer, such that it shouldn't be equals to 0, like the one here, right? So you notice that PV plus QT over QU, these are all integers. So an integer plus another integer divided by another integer is still going to be an integer divided by another integer. So that part you don't have to prove. That's why they say informal proof, you can cut down on the working because it's already assumed. And then, therefore, our conclusion is the sum is also rational, right? By this representation. So a lot of questions will either be like the earlier case, you just work step by step, or you're having to use or introduce new variables or unknowns into your equation, and then you can go about proving it. So, proof by contraposition, like I said, is your indirect proof. And here we assume the negation of Q, and then we show negation of P. Why do you have to do that? Because in some instances, we cannot find or how to go about proving for Q, because we're only assuming P is true. So when we assume P is true, we don't have to show working for P. But in the case that that cannot be done, then we have to look at the alternative. Conversely, we look at the contraposition. So in contraposition, we say that negation of Q implies negation of P. So now we just have to focus on the state of P by just assuming the state of Q or negation of Q is already determined to be valid, right? So prove that if n is an integer, then if n is an integer and 3n plus 2 is odd, then n is odd. So in this context here, your P is saying that in the two states like this, where n is an integer, and then that integer times 3 plus 2 gives you an odd integer, show that n is odd. So how are you going to show n is odd? You don't know where to start from because that's your Q. So the best way to do is to use a contraposition or an indirect proof. Direct means P implies Q, indirect means to get the opposite conversely, right? So here is very straightforward, isn't it? So it's the same case. So in indirect proof or contraposition, always remember, don't state it in its positive state. You need to put it into its negative state, right? So using indirect proof, we have to assume that n is even. And then we have to say that now we have to prove that kn plus 2 is also even, because the original premise is odd. It is an odd number. So when you negate it, it then becomes not odd. Sometimes I just call it as not odd because some books, when they give their proving, they use it as not even or not odd to keep it in its basic form of negation of P or negation of Q. So you don't get confused when you're doing the here for this one here, we tend to use the slides, they tend to just use it as the state of it, not the representation of it. So in the indirect proof, we're trying all proof by contradiction, and the assume now is we're assuming that if I cannot write, what I'm going to do, second, then can't be the battery of the pen. So now I'm going to assume that n is not odd, which means it's even, then what? We have 3n plus 2 s is not odd as well, because it's a negation of q implies negation of p. So this is also a case of even. So now our end goal is to get an even number or the representation of a 2k, right? So assuming n is odd, we have n equals to 2k plus 1 for some arbitrary integer k, right? And then we have 3n plus 2 equals to 3 times 2k plus 1 plus 1. And then what we get is 6k plus 3 plus 1, right? To give us 6k plus 4. Sorry. Did I get it wrong? N is odd. It should be odd, isn't it? I did it wrong because n is not meant to be it's meant to be an even number, but I'm getting an odd number, so I did it wrong. It shouldn't be odd. Not bad. It should be even. And then the outcome should be even. So when even, then right, n equals to 2k. So 3n plus 2 is this. So this now becomes 3 times 2k, which is 6k, right? But remember the question says that you have to show that it is even. So again, you just have to factorize it. We get it as 2, 3k plus 1, and this is in the form of 2j. Hence, we have proven that 3n plus 2 is even. Hence, the original statement, if I setting screen and white, if we have the case of n is an integer and 3n plus 2 is odd, then n is also odd, right? This is using indirect proof. Understand? So you get the difference between direct and indirect. Huh? Indirect always the yes.
When do we use this indirect proof?
In a lot of cases, the question itself will request you to use it, right? Just you see the books and all, normally when they give the exercises, they always say use indirect proof, or commonly they'll say use proof by contraposition or proof by contrapositive, right? That the following argument, the following statement is valid. So that's the time. If it's not stated, they just say give a proof, right? Or prove or disprove the following. Don't go and disprove it, because it's harder to prove something is false. Always try to prove something is true. Then it's up to you whether you want to use a direct or indirect. A lot of cases, use the direct first because it's so easy, so straightforward. Unless there is no way to try to get the answer using a direct, then you go about using the indirect. Because like in this case, there's no way you can just come to a conclusion and it's odd. How are you going to prove this Q is true by just assuming the first one is true? Because we cannot prove the first one in a direct way. There's no proving for the first one. Only for the Q you need to prove. So you say n is odd. N equals to 2k plus 1. So what is k? You have to give an instance. Then you have to give a negative infinity all the way to infinity. So two scenarios. If you want to do it on your own, the question doesn't state which way. Then you choose it in the appropriate context, or like whenever the question asks for it. Okay?
Okay, thank you.
You're welcome. So here we have shown the negation of Q, blah, blah, blah. So that's actually to explain earlier. Please, my brain said it wrong. So Now, prove that for integer n square is odd, then n is odd. So here, okay, now in this question, it didn't even state whether it's direct or indirect proof, but you already can see that p refers to n square is odd. Now we're going to assume that as odd. How we're going to prove n is odd? So we have to use an indirect proof. So using contraposition, we assume it to be not odd, or assume it to be even. So if we assume n equals to 2k, we have n square equals to 4k square equals to 2 times 2k. This is in the form of 2j. Hence, we say that it's an even. N square is always even. So using so we say that therefore by contraposition, or therefore by proof of contraposition, for an integer n square is odd. If n square is odd, then n is odd. So your conclusion shouldn't refer to the working that you've done, the state of it. You always have to go back to the original statement, right? Use the definition of even integer and odd integers. Give a proof or contraposition for the following statement. If 3n minus 5 is even, then n is odd. 3n minus 5 is even, then n is odd. Again, we're going to use proof by contradiction, right? So here we say assume n is even. So we're going to get the case of n equals to 2k for some, you have to write this out for some integer, arbitrary integer k, or some arbitrary integer k, lj, or whatever to use. So we have n equals to 2k. And the next step would be 3n minus 5. So 3n minus 5 equals to 3 times 2k, right? Minus 5 to give us 6k minus 5, right? So in the case of this, we can rewrite this as what? Now remember, the goal is to show that it is, oh wait, I got it wrong, isn't it? Assume that 3n is even, then n is odd. So we are flipping it for contraposition. So we say that n is an even, so it should be n is odd. Oh, I did it wrongly, because we're flipping it. So this is even, this is odd. So I'll look at it correctly. But if you use this way as well, we'll still eventually get the answer, but it's the wrong method we're using. It should be n is odd. N is even, correct, isn't it?
But if you continue that way, then after that we just prove that 3n minus 5 is odd, right?
Yes, correct. Yeah. If n is odd, then 3n minus 5 is also odd, right? I got it. But yeah, it's correct. I mean, the one I was doing is so correct. I just looked at the top bit and I confused myself. I mean, the one on top here. That's stable. We have n equals to 2k because we're looking at your q being not odd. So when you prove it as 3n plus 3n minus 5, right? It's minus 5 here. We find that it is in the form of 6k minus 5. Now, remember, negation of p should be odd. So you have to get 6k minus 5 to look like an odd number. That means we have to make it look in the form of 2j plus 1. Don't give it some other form. 2j minus 1 is also a negative number. 2j plus 3 is also a negative number, right? Because the very even number plus 3 is also a negative number. Don't do. Just keep to the basic one of 2j plus 1 or 2j. So to get that one there, it means that we have to have 6k, and also because we need to factorize for the 6, right? So we have minus 5 plus 6 minus 6 to give us your 6k plus 6 plus 1, and this is in the form of 2j plus 1, right? Where j equals to k plus 1. So we have the 6k plus 6, so in case for those who still or just with your rusty algebra there, right? So it's 6k plus 6 plus 1, so you get the 2j plus 1. So hence we are proven to be true. Simple as that. So using proof by contradiction, we have shown that if 3n minus 5 is given, therefore n is odd. So that's for the question. That's all the explanation there, I think.
Sir, 6k
Yeah.
plus 6. Is it?
Yeah.
Plus 6k.
Yes, 6k plus 6k plus, because I'm just introducing, I'm just trying to factorize it in the form of 2j plus 1. So we have the form of 6k now minus 5, right? If I'm going to plus 6 minus 6, this is going to become 0, right? So now I'm taking this 6 to put together with here. So then I can get the 2j. And then what happen? Sorry, not 6k, shouldn't be 6k plus 6, it should be 6k minus 6. So this plus 6 minus 5 gives us the plus 1, so it's 6k minus 1. So this is 6k minus 1, sorry. But then you get it in the form of 2j plus 1, where j equals to k minus 1 now, or 3k minus 3. So we have it in that form. So how you work about that? Even if you want to plus 12 minus 12, you're still going to get something like this, right? Or can you do like, then you have to still like add on because it's a plus 5 minus 12 and all that. So anyway, that is on that one. 3k minus 5, blah, blah, blah. So same thing, 3k minus 3 plus 1. Yeah. Therefore, 3n minus 5 is odd and hence it's not even. So now, proof by contradiction. Now, this is where it becomes very interesting. So it's also known as reductio ad absurdum. That means, in other words, you're trying to say that the opposite cannot happen, right? So to prove P, we have to assume negation of P, and then we derive a contradiction such that P and negation of P, which is your indirect form of proof, right, is what? If negation of P is false, then P is true. So we assume negation of P to be true. So if negation of P to be true, then P is false. So think of contradiction like when somebody said that, oh, the earth is round, right? And you say, I don't believe you. And the guy said, prove it. So you have to prove by contradiction. I'm going to prove to you the earth is flat. So when you are going to prove to that person the earth is flat, you have to assume that it is valid, it is true. But your outcome becomes false. So now because it becomes false, therefore you have to give in and say, yes, I concur with you that it is true. That earth is round. Understand? So that is how we look at approaching proof by contradiction. So because all this, you notice that the earlier slide on the explanation of that and the one here, it doesn't, it's like, it's all like Rojak trying to explain to you. So the best thing to do is actually to look at how you can use a pen while trying to, right? Try to make it look, to look at examples, okay? So prove that if you pick 22 days from the calendar, at least 4 must fall on the same day of the week. This is a pigeonhole principle question, right? So now, what is the original statement? You are going to take 22 days, and from the 22 days, you say at least 4 must fall on the same day of the week. So proof by contradiction, say like you say that, oh, at least 4 days must fall on that. And you say, no, I don't believe it's at least 4. So if you want to prove the opposite of it, right, you have to prove at most 3 of the 22 days must fall on the same day of the week. at most 3. That means maximum 3. So it can be less than 3, but at most 3. So if we look at most 3, we know that in a week there are 7 days. So 3 days that fall on the same day, on the same day of the week, would be 3 times 7. So there are 21 days, from which 3 of it will fall on the same day. But here you have 22 days. So therefore, it is unlikely that at most you will get 3. There is still that possibility of it having the 4th day occurring at the same time. Understand? So 1 week is 7 days. So these are all the 7 days. So this is the 1 week, this is 2nd week, this is 3rd week. So at most you only have 3. But now, this is 21 days. The 22nd day would have to fall on one of the 7 days. So hence, you have proven that using proof of contradiction, that at least 4 days must fall on the same day of the week if you are going to pick 22 days, right? And that's the explanation there. So always think like you have a case like this scenario where it shows at most, at least, then look, is it like when you say x is greater than 0, then it has to be x equals to or lesser than 0, because x doesn't assume the value of 0. Likewise, when x is lesser than 0, then the negated form will be x is equals to or greater than 0. So the negated form must be careful lah, don't do wrongly. So use a proof by contradiction to show or to give a proof that the square root of 2 is irrational. So now this is tricky because they just say square root of 2 is irrational. So how are you just going to put that? So remember, this is using contradiction. So I'm going to show that if the square root of 2 is irrational, I'm going to show that it is not rational. Then it has to be in the form of a rational number. Then we are able to introduce, remember the earlier case, we have x equals to, that x equals to p over q. Because we do not know the form of an irrational number, or we know that a rational number is in this form. Anything else is not a rational number. So using proof of contradiction now, we assume negation of 2 to be rational. So if you're going to assume negation of 2 to be rational, it is the case of it being represented by 2 integers a and b, where b cannot be equals to 0. And they cannot have common factors, right? So that means you're not looking at multiples of it. So square root of 2 equals to a over b, then 2 equals to a square over b square, and then we get the case of 2b square equals to a. So therefore, a square must be even, right? A square is in the form of 2k, right? So if a square is even, then a must be even, right? Because even number squared will always get an even number, and conversely, so a squared even number always will give you original number as even. So if a is also even, then you can say that a equals to 2c. So now we get the case of 2b square equals to 4c square, because from here we get it as 2c square. So 2b square equals to 4c square, then we get now b square equals to 2c square. So again, b square is an even number based on an arbitrary integer c, right? So if b square is even, then we also know that b is even. But then 2 must divide both a and b. This contradicts our assumptions that a and b have no common factors. Hence, we have proven by contradiction that our initial assumption must be false, and therefore the square root of 2 is indeed irrational. Understand? So this is a bit you need to like know your number theory well. So here basically what you've done and eventually proven is if A is even, B is even, it is not a rational number because they cannot have this common multiple, right? An even number divided by even number will always have a common multiple, right? It has to be a unique one, like 3 over like pi, right? And whatever. So since this is the case that it violates the assumption of your rational number, therefore the only conclusion is the original statement is true, which is square root of 2 is irrational and not rational. So that's that one. So don't think too much about that. Easy don't ask questions which is that too deep of thinking. There's no time for students to do it in exams. It will take at least 2-3 hours.
Thank you, sir.
So you're welcome. I try not to ask questions which are too difficult because we have to balance between the different the skills in knowing your number theory when it comes to proof. So normally if you do enough exercises like in the tutorials and all that, then it will be sufficient to do any proof questions that come up for exam. So give a proof or contradiction that this statement is true for all integers n. There is no integer x and y such that x squared equals to 4y plus 2. So now you have to know what's your p and what's the q. There are no integers x and y such that x squared equals to 4y plus 2. So you say that if x and y are not integers, then x squared equals to 4y plus 2. So x and y not integer. Alright. Then we have the case of 4y plus. So if we're going to use contradiction, again, what are we going to assume now? Do we always assume the conclusion or the consequent as false and then we prove for p? Or we actually prove negation of p is true and then we have to show that the conclusion is not true or the consequence is not true. So you can do either way. That's the one I say where it becomes confusing when you look at certain books and or it's when they call it as a contradiction. So the contradiction can occur in two ways. When you put it into a contrapositive form and then applying the contradiction, or leaving it in its original p implies q and then applying negation of p assuming that q is true and proving that that cannot happen. Right? So it can happen in both ways, where you look either the antecedent or looking at the consequent, but you're going to make sure you're putting it into the right form, so you don't end up just doing the wrong method, which is just using contraposition, right? So in this case, we are going to look at what? Saying that if x and y are integers, right? If x and y are integers, then you have to show that x squared x squared equals to 4y plus 2. There are no such integers x and y such that x squared plus equals to 4y plus 2. So we have to say that there are integers x and y such that x squared equals to 4y plus 2. And then we show that it doesn't happen. So we proceed by doing the following contradiction. Suppose there are such integers, right? So such integers, how would they exist? They have to exist over x and a y. Here they just simplified it for a reason. So x squared, we know it's an even integer. So here you're going to see they are going to break it down until you're able to find that x value and that y value, or they're trying to find a property of x and y that would then say that it is not an integer. So here what they do is by looking at the q. The q is x squared equals to 4y plus 2. They factorize it like that, so we see that now x squared is even. If x squared is even, we know that x is also even. If x is even, then we say that x equals to 2k. And subsequently, we now can have the form of x squared equals to 4k squared. So if x squared equals to 4k squared, in turn, this says that 2k squared equals to 2y plus 1. Right? So that is getting the one in here. 2 times 2y plus 1. So you have your 4k, which is same as 2k squared equals to 2 times 2y plus 1. So if 2k squared is even and 2y plus 1 is odd, then we know that it doesn't make sense, isn't it? The left hand side and the right hand side. So this is a contradiction. So this is another form of contradiction. You don't have to say that the conclusion doesn't contradict the original P. Here we are saying that in doing the proving, it's a contradiction because it cannot exist when you're making the assumption. So here we're saying that when we had it as x squared equals to 2y plus 1, right? We're saying that x has to be an even number because of the form of 2k or 2j. Then if x is meant to be an even number, so we say now this is a y, so we leave that in. So we have the 2k squared to give us this form of 2y plus 1. And still there's 2 outside, and then we're going to get the 4k squared, then we factorize it to cancel off the 2, and then we get 2k squared. So whatever k value is times 2 is an even number, and the other side, whatever value of y times 2 plus 1 is always an odd number. So then an odd number will equal to an odd even number, hence it's a contradiction. So by proof of contradiction, we've shown that there are indeed no integers x and y such that x squared equals to 4y plus 2. So you see, this contradiction here is you are going about trying to show that such integer exists, but end up showing that it does not exist. Right? Earlier case is you're looking at the negated form and saying the negated form. For the earlier case here is again something like that, right? That you will not find such rational number, right? That such rational number wouldn't exist. For this, I think there's one more example.
So here we started with negate P, is it?
Yes, for the negated P. The earlier one is
x, y is an integer.
yes.
Okay.
So here we say that there's no such integer, so you say x and y is not an integer. So negation of P would be there is such integer x and y. And that's why we went about looking. This case here, the earlier one is we're assuming, right? What are we assuming here? What is the P and what's the Q here? Suppose the square root of 2 is rational. So again here, we are trying to say that the square root of 2 is not rational. So that's again a negation of P. But the way we work with it is we're assuming that the conclusion is that you're going to get as in like the Q is not a rational number. So I think there's one more example like that. Let me see whether it's towards the end so then you can really see the difference. So for biconditional condition, right, it's very easy. You have to prove P implies Q and Q implies P, because we know that the biconditional statement P if and only if Q is logically equivalent to P implies Q and Q implies P, because this is a very strict implication, we say, right? P must imply Q and Q must imply P. So both has to be true. So unfortunately, in the case of any question given for here, you have to do for both. So for this question here, you see, prove the theorem that if n is an integer, then n is odd if and only if n square is odd. So here the p is n is odd, therefore q is n square is odd. So you have to show that if n is odd, n square is odd. We already showed that earlier on. Now you have to show for the case of q implies p. What is q implies p? Q implies p say that if n square is odd, therefore n is odd. How we do that? It's given here. Sometimes this can be used as abbreviation of blah. You should previous that both p and q. Did we do q implies p? I don't remember doing that. But yeah, for the case of p implies q, straightforward. For the case of q implies p, when you say that n square is odd, assuming n square is odd, then n is odd. Really shown that, but all you can do is to then use proof by contradiction or proof by contraposition. So for this part here, when you're trying to prove this, you just use proof by contradiction. What is the proof by contradiction? It will say that if q implies p, then it's going to be negation of p implies negation of q. So going back to if n is not odd, therefore n square is also not odd. So that's how you go about doing that. Sometimes you are given questions where they ask you to look at the steps and whether it's true or false. So we have, whether the steps are correct. So here we have a equals to b. So that's a premise to say that you have the proof for 1 equals to 2. So let's say we start with, we have an integer a, we have an integer b, and we're going to say a equals to b, right? And then we square a square, we're going to get it as a times b, because a square is the same as 1 of a can be equals to b, so you have it in the form of a times b. So then you say a square minus b square equals to a times b minus b square. So here we're just introducing the minus b square, and then we can factorize this to be a minus b, a plus b, and then on this side we factorize it to be b times a minus b. So then you can cancel this off here, right? So you get a plus b equals to b. And then what do? You just take again the earlier one case of a equals to b, you put that in here, you're going to get 2b equals to b, and therefore you have proven 2 equals to 1. So now we know that doesn't make sense, that is wrong, and which step is wrong? So the working looks valid, right? Or the proof looks valid, but we know that it is not. And where is that? Where does that occur? Now it occurs when you're doing this kind of algebra. You always remember that introducing your variables into the equation randomly cannot occur, especially when you've already done the simplification on this side. Or you factorize it. So now step 5, a plus b equals to b, right? So a minus b equals 0 by the premise, and we know that 0 cannot be or cannot actually occur, and that's why I said the simplification for step 4 cannot actually happen, because you're just assuming that you can cancel out the effect a minus b, a minus b. But in fact, that a minus b at this point must already apply this one here, right, to get 0. So that is where you know that this argument is wrong, because in simplifying, sometimes we forget certain aspects or certain contexts of the properties of your variables or numbers. So looking ahead, if direct methods are already towards the end of this part, if direct methods of proof do not work, we need to use clever ways. Like we saw earlier for the biconditional, we already know directly if we can prove P implies Q. But we're trying to show for Q implies P. How? So we use contraposition. So then we can get back a different version, the alternate version of P implies Q, which is negation of P implies negation of Q for the other part of Q implies P. So we go quickly. There are proof methods. So proof methods we already saw earlier on. Now we look at the proof strategy. So your proof strategies are basically when you cannot use just one direct method or just a vacuous proof or trivial proof whatsoever, you have to use a combination of it. So those combinations of it is examples would be proof of cases where for odd numbers, for even numbers, then different ways you have to use. One is using contraposition, the other have to use a contradiction, right? Existence proof, we don't usually use it much. The other one I mentioned was the disprove by counterexample, right? So when you have a scenario of say, please prove this is true, it may not be true. Or say, disprove that this is that using a counterexample. So they're always focusing on, or examples on looking at counterexamples. See, they always say, use a counterexample. Or else you're just going to waste time having to go through and through a long time to try to prove something that actually isn't true. Right? So disprove by counterexample is where that would be stated. So this quickly, like here, prove by cases, you're just proving all cases. So example here is show that in the case of determining the maximum value of two integers a and b, we know that the maximum value equals to a whenever a equals to or greater than b. Otherwise, we say that it is b that is the higher value, right? So show that if a max b max c is the same as b max c max a, right? So it's very easy. You just have to show that for the first case, whenever a is greater than b, at the same time b is greater than c. Then we have the case of a is greater than c, but c is greater than b, blah, 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 all the 6 cases. And actually, case 1 is the only one you have to prove because all the other cases are exactly the same method. So in case 1, we just show that a and b, if a is greater than b, a is the result. Now, when a is a max c, we know that a is still greater than c. Finally, b max c, we know that b is greater than c. Therefore, a, b, c is the same as a. And likewise for the right hand side, b and c, this is b, then a max. B is still a, hence that one. And the same thing is going to be repeated for all the other 5 cases. So that is the form of case by case. So a counterexample is just finding one event of one instance where it will not be true, right? So remember that we have the form of there exists an integer x such that negation of px is true. And this is the same as in no case of px is true. Negation of ax, px. So we establish that no values of x such that px is true, right? We say that for all values of x, px is false. We have to find a case such that negation of pc or pc is false. So that is trying to say the opposite occur, right? And in case is every positive integer is the sum of the squares of 3 integers. The integer 7 is a counterexample, so the claim is false. So that means you only have to find one instance of it, so then you can say totally false. Here we're trying to just substitute the value lah. A positive integer is the sum of the squares of 2 integers, any positive integer. So you just show that 7 is not, because 7 is actually a prime number. So any prime number would only be derived from itself and no other composite or prime numbers. So yeah. And here, proof strategy, to just explain it, you first try a direct method like I said, and then if it doesn't work, then we try to use an indirect method to see whether it's we're able to obtain the answer. So for whichever method you're trying, choose the strategy well. So first we do what is known as a forward reasoning method, and then when it does, then we use a backward reasoning method. So what it means by forward reasoning and backward is very simple, like what your friend did just now, when talking about that extra example, right? You already know the working from one way, so then you try to show it by reversing the steps to say, like, what if I try to do like this? Would I be able to get the answer? Right? So forward and backward reasoning. So forward reasoning means you start from your S1, right? And that S1 is derived from your P, right? And then an S2 is derived from S1. And finally, that Sn is going to derive our conclusion Q. A backward reasoning now means you have to go backwards. So you already have your outcome. What is the one step behind that? And what was the previous step behind that? And until you reach your beginning, right? But when you are writing down the proof, you do it in a forward method, right? So that's I already summarized the whole thing, so you don't get that part. So example here is to say for all values of a which is greater than 0, and for all values of they didn't put for b, so then we just say for any positive integer b, as long as they are not the same, so then we call this as none. What would you call this? A0. Okay, now I made a mistake. Here in the slide, it's not clear because it should be like this. So this quantifier is referring to both a and b. So we say that this is a non-negative integer, right? A is greater than 0, b is greater than 0, they're not negative. So we say that for any non-negative integer a and b, and now a not equals to b means they are distinct. So we say for every distinct integers or non-negative integers a and b, a plus b divided by 2 is always greater than ab to the power of half, right? Now, why this definition came in and in this very restrictive form is because we have the case that later on you see something is going to be divided by something, so it cannot be at 0, or it cannot be the same value, right? Which is here. So there's no obvious way to start from here, isn't it? How are you going to say, oh, from a greater than 0, b greater than 0, a not equals to b? How are we going to work until we get a formula like this? There's no way. So we do backwards. So if we do it backwards, we know that a plus b divided by 2 is always greater than ab to the power of half. So from here, if we square both sides, we're going to get it as a plus b squared over 4 is greater than ab. And then we're going to do what after? Or then we just take the 4 and chuck it to the other side. So because this is over 4, so you just multiply by 4, and then you're going to get the case of a plus b squared. So when you expand that, you get a squared plus 2ab plus 2b equal greater than 4ab. And then you take this one, you plug it onto the other side, you're going to get a squared minus 2ab plus b squared always greater than 0. And we can now factorize this. You expanded it earlier, now we're going to factorize this. We're going to get it as a minus b squared is always greater than 0. So in this form, we now know that whatever the value of a and b, when it's minus and squared, will always be greater than 0. So, as long as, that's why I said earlier, as long as a is not equals to b. Because if a equals to b, this cannot happen. It's not equals to 0 or more. It's greater than 0, right? So, we know at the same time this is not equals to 0, hence we get the case of a is greater than 0 and b is greater than 0. So therefore, we have come to that conclusion that the statement is true. But when we are writing it down, we have to write it in the opposite. Right? So since we start by coming up with a story, we say that a is not equal to b, a minus b is not equal to 0, then because a minus b is not equal to 0, therefore a minus b squared must always be greater than 0. And if you expand this, we get it like this, and then next thing you know, I reach the end. So backward reasoning is that way. You work backwards, but then you still have to give the story forward-wise. So essentially, that is just that, right? And all this like blah, 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 this one, all it's because you work backwards to show it forward, right? So that's an example there. We don't really use a lot of backward and forward reasoning. I usually, if I ask exam questions and everything, normally it's just on the basic proof methods, right? It's just to explain here. So the stone game is Chongka, right? And Chongka is very straightforward, right? Chongka is how are you going to end up always winning the game, right? So the first thing you have to do is make sure that you're the first player, and you take a certain number of the marbles. Then whatever the guy take, he will always be at the losing disadvantage, the losing end. So you can go and read up on that. This will take a while to explain, but it's how you actually say that you take any multiple of what? 4. Yeah. Because you have to take 12, and then from 12 he takes the maximum of 3, then it'll always be 11. You can take a maximum of 3, blah blah blah, until there's only 1, 2, or 3 for you to take. So that is that bit there. Oh, it has actually been recording this as well. I didn't know that. I mean, PowerPoint was recording it as well. So anyway, we come to the end of this chapter. I think this is all I can do for today. I tried to like squeeze all in by 3 hours. Unfortunately, couldn't. So, but thank you very much. Any questions?
Fine, sir. Thank you so much.
You're welcome. Because there's only 10 minutes left to 6. Yes, do you have a question?
Sir, do we have another extra class or?
No, I will put everything in a video lecture. I think it's not fair to have to impose a class on you all. So what I do is I will put the video lectures for all the remaining topics. The remaining topics after proof is induction, relation, graph, and trees. Wow, still a lot.
Sir.
But no.
So I have a question about the contradiction one. So I can
Alright,
start
yeah.
from either consequent or the antecedent, right? I just negate one, and then what do I do?
Yes. Okay, so you see. Now, give me a second. I have a battery issue with my 25 minutes. Wow, 3 hours. Was not being charged. Hang on, Alright, so now you see in the case of what you mentioned, when you look at pause this because it's going to go haywire. So now in what you're trying to in your what you ask again. So for a contradiction, always remember it's in the form of negation of P, assuming to be true. And it will never be the case that negation of P and P being true. So that's a contradiction then. So when you're using either the antecedent or the consequent, you want to use the consequent, which is Q, because it's easier to do that. Then to assume Q is true, you have to put it into the contrapositive form, which is negation of Q implies negation of P. So that's where we say, we assume now Q is true, and we have to show that negation of P is also true. So you understand?
So I just assume Q first, then negation negation of Q implies negation of P.
Yeah. No, you don't assume. You have to think. One is the format that is being represented. What is coming first before the other? So when you say P implies Q, it is. Y'all can hear me, right?
Yes.
Okay, yeah. I need to
Yes.
stop there because when I exited from the projection, WebEx picked up. So I thought it froze already. So anyway, I use a whiteboard that you can see that. Whiteboard, share whiteboard. So in the original form of contradiction, we say that P is P implies Q, right? So contradiction, we have to assume negation of P. The negation of P is, what do you call it? Sorry, negation of P is true, right? And then just go about showing Q in that form of negation of P is also true, right? So when that doesn't occur, then we know it is a contradiction, right? Because if we just assume negation of P is true, we have to still work for the Q. In the other form is because P implies Q, so the other form that we can look at is when negation of Q implies negation of P. So now we are trying to say, we assume still the antecedent, the opposite of the antecedent is true. So your antecedent is negation of P, so now we're trying to assume that Q is true, therefore negation of P has to be true. But it is not. So you see the difference? Here now we have to, so the burden falls on proving P is not true. Negation of P is not true. In this case, when we assume negation of P, the burden is to show that when we're trying to prove Q, Q fails to be true whenever we assume this to be true. So that's the two way of looking at the contradiction, or when we're trying to apply contradiction. Right? You see some examples. Why are they just not looking at Q? Why are they just looking at P? And to say that if P is odd, suddenly your answer, the working shows P is even. So that's a contradiction there, because it's based on something like this one here. Understand?
So for the second one, right, negate Q implies negate P is a contrapositive, right? It's equivalent to
Yes.
the P implies Q. So
Yes.
we have to prove that the negate P is not true, which is P, right? Like you said, is it?
In contradiction, you have to assume that your antecedent is true, right? In contradiction, proved by contradiction, we have to assume now P implies Q. Contradiction say that if we to look at the alternative nature. So what is the alternative nature? The alternative nature of it is that negation of P is true. Because we know if negation of P is true, this has to be false. So if this is false, this is true, it's still true. It should be false. So this negation of P has to be false, not true. Because remember, P and negation of P cannot be, cannot exist. That's the slide I'll show you. Both cannot exist like this. P and negation of P cannot be true. That means it's a contradiction. Both states cannot give you the same answer for Q. That means I actually say that P says n is an odd number. Therefore, n squared is also an odd number. So n is odd, n squared is odd. So contradiction says now I'm going to say that n is not an odd number. So n is even number. So the law, when you do your proving, you cannot find that Q exists, because it's earlier on you prove and shown that, you know, odd number leads to a squared odd number. You cannot say now that an even number squared can lead to an odd number, because Q still remains the same. So in using a contraposition, so we're just swapping it now. So the burden now, instead of having to show Q's working, we are just assuming the nature of Q to be true and just showing the original instance of n. Like in this case, n lah, but actually we're looking at the negation of P. So here, remember, when we negate it like this, we then have to assume that the antecedent here is true. Change color. Keeps giving me arrows. This is really whiteboard, one. So it has to give you Can't write already. Give me my pen back, please. So now you have to assume that this one is now your antecedent. So in its original form of negation of Q implies negation of P. So proof of contradiction would now require you to assume that Q is true. So when Q is true, then negation of P has to also be true. So you're proving for that instance there. When Q is true, negation of P has to be true. But when you're doing the working, you will never find negation of P in that state. It will never be true.
Oh,
So
I get it,
therefore,
sir. Thank you.
So that's the contradiction there now. Any other question? If no questions, then I think I'll end here. I will upload the video lectures all today. What I'm going to where I can recycle what I've done last year, my video lectures. I'll do that because some of them are split. Some are already in one full video. So I will upload that as well as the one on for the past semester, what you've done so far. I already downloaded everything, so I'm just going to give you the link for that. Anyway, how was the test on Sunday? Was it too difficult?
Yeah, so I think there's an error for the question. There's a question consists of pictures, and then the answer also consists of 4 pictures, but then all the pictures is not cannot be seen.
You see, if can I show you my test bank question? I don't have that problem. I don't know why it occurs. In my side of the test bank, it's there. It appears. These questions were questions which I took a whole day on Saturday to go through over and over again to ensure I don't get that complaint. And it still occurs. I do not know why, honestly. And without those pictures, there's no way, because I just can't represent it in text, right? It's too much, because it's using mathematical formulas and all that, right? To put it into text form. But yes, on my side, if I can show you, that is my text bank. So I don't see the error there. And I even swap using different browser. So it only leads to that question whether you are using your phone to do the questions or not. Second thing is, I don't know how, but if you do not log in with your identity, the Unimas identity, you should be able to see it. The only way that eLib doesn't show you is because you're not logged into eLib. Because the image belongs in eLib server. So if it's not showing, it means that you're not logged into it. So I really do not know why that is occurring. But yeah, I would go through it again and I'll see. I can show you the results on that, but I know a lot of you show me screenshot, but I realize it doesn't occur for everyone, does it?
I think so. Some of them doesn't get the question lah.
Yeah, because it's a random question.
Yeah, but I also use laptop and log into Unimas, but still cannot see the pictures.
I got to go check this with Calm, because you see, it's not what I do is I just use my question bank, and you know the import function inside the eLib, which is using a Moodle. So this issue, I think I have to bring it up with Calm and see, why, because they asked us to do this, just do this. So if there's anything that is, like an oversight, they should know of it. Why is it occurring for me like that? But these questions are new questions which I uploaded Saturday. As in, because I get questions like this before, I've re-uploaded from the original source. And if it's still doing that, I have no idea why. So I can only think it's because, but if you're going to hold over, it shouldn't be an issue. If it's from, let's say, exam website to Ellipse website, then yes, I can understand that. But all this is because of that. I think it's the universal login thing that the new thing they've introduced. Previously, we didn't have that issue. So what I'll do is, I think I know which question is that one. I will cancel this question, and the marks will be readjusted for images. Yeah,
I also got chapter 5 questions inside the exam.
chapter 5.
Yeah, I got chapter 5 questions and some other people also did. Yeah, it appeared in the exam.
What you mean chapter 5?
Proof. I got some of the questions at the exam.
The proofs inside. I already went through it. There was no proof.
It appears in the exam. I can show you that, sir.
All right, but what was the question again?
I don't remember them, but yeah, there were quite a few of them, like 5 questions at the very least.
Oh.
There's
More than
I
half.
remember a
talk
question
about
about
modus
the
tollens.
modus ponens there.
Oh, okay. I know. Yes. Oh, sorry,
Yeah.
but I think that was that's not chapter 5. I thought it was still under chapter 4. Isn't chapter 5 on proving?
But sir, that we just learned modus tollens just now.
Oh yes. I think that was my side because of the way I categorize the question. Oh yeah, so I think I have to look into it. I thought that I didn't include modus tollens in that. The questions probably kept inside because I had two different sets of test bank that I was using collectively. I mean together for your exam. The one I did on Saturday was the one that I vetted through, and I remember putting ontological equivalence law. So that's why when you said the one on proving, I thought it was called disproving here. I didn't. But for modus tollens and all, it's under rules of inference. I'll go back and check on that and see why it occurred. Probably it was attached to the other question bank that I was using, which was not meant to be this type, but I think I know why. Yeah, the question is actually under that one. The special questions, I think. Yeah, I'll go back and check on that. Don't worry about that. All right. Anything else?
So we don't have this is the last class, is it? We don't have class for
class,
Thursday.
yes. Yeah. No.
Okay.
No. What I can do is I don't have a session where I just want to look at past year exam questions. I think when I do that, yeah.
Also got question about when our final exam.
Do you all have a schedule yet? Was the schedule given out already to y'all? Your exam schedule? Yes, right? So then you just follow that up. Because normally, you see, on my side, right, the exam, right, the date sometimes can change. So the onus is on you. I don't really pay attention to when the exam class is. I mean, when the exam date is, right? Unless it's just before I'm supposed to set it for the system. So I remember when I told you all like I wanted to look at using exam as that backup. I mean, like as a practice for y'all, they still haven't opened it. That means in the system, it's only showing my past 2 semester for the exam. So that's why I can't enable y'all to go into exam.unimas.my to trace it out. That means you haven't opened up the period for us to let you try it. If that occurs, I will just put a dummy one inside. If it needs to be, then you all can do it. So what I'll do is this Thursday I can wait up. Give me a second, let me just check. Because I have things that I've already planned for this week. Sekejap ah. 2. Semester break is on Thursday. Oh no, I made a mistake. Sorry, I made a mistake. So I'm looking at the wrong. Am I looking at the right calendar in my phone? On 22nd, I'll proceed with the class this Thursday. There'll be a class this Thursday then. I'll keep it to that. So we'll meet back again on Thursday, which is the 6th of January, isn't it? Yeah, class will be usual at 4 p.m. And then I will decide after that. For the assignment, it's still due on the 7th. So yeah. But test 2, I'll go through it and then I'll get back to you all on the outcome. Okay, I need to see the extent of I suspicion it's the calculated type of questions that I added in, not the standard MCQ ones. Or probably it was a standard MCQ question for that thing where you say you got the modus ponens and tolerance and all that.
Yeah, sir.
The standard one, huh? Good. Maybe I need to I'll get back to you all on that one.
It's okay,
So if
sir. Thank you.
yeah. So if nothing else, then thank you very much. I will see you all this Thursday. So Thursday there will be a class, as usual.
Thank you, sir.
Okay.
You're welcome.
Thank you, sir.
Bye.
Thank you, sir. Bye.
Bye.
Thank you, sir.
Thank
you, sir.
You're welcome.